So we're going to start off with sequences, both arithmetic and geometric, which we'll do half today. We'll do geometric tomorrow. But you've seen this before. Might be a little review. If not, don't worry. It's going to be very similar to stuff we've already done before. All right, so one of the most famous sequences is a Fibonacci sequence. I don't know if you've seen that before, but you add the preceding values to get the next value. So 1 plus 1 is 2, and 1 plus 2 is 3, and so on. And it leads to something pretty cool called the golden ratio or golden rectangle. So that's just one possible sequence of numbers. So that's all it is, a sequence of numbers that just keeps on going with a certain number assigned to each one. You know, very plainly, the first number is called a sub 1. The second number is called a sub 2 and a sub 3. And you want to think of these 1, 2s, and 3s as like the x values that you plug in, and then you get a y value or an actual sequence number in return. All right, and you can have several types of sequences. You can have an infinite, which of course goes on forever. So anytime you see that dot, dot, dot at the end, which is called an ellipses, anytime you see that at the end, right, that means it's infinite. So that dot, dot, dot means it keeps on going without ever stopping. And then there's the opposite of infinite, which is you just take off the in, it becomes finite, but you pronounce it finite. So finite is the opposite of infinite, and that would be something that just starts, let's see, 5, 8, and then 11, and there's a number at the end instead of ellipses. So if there's just a number at the end, that's how you know it's actually finite. It stops off. It gives you a first term and a last term. So you know for sure it actually does stop and it's finite. All right, so a lot of this is going to be just language and how you write things down more than how difficult the problem is. So just be thinking about, well, this is similar to that, but we write it this way when we're talking about sequences. So a few things. We usually talk about the first term, or the second term, the third term, the fourth term. The general is the nth term. So if they say nth term, they're talking about what number term are we looking for. Okay? Sometimes you use k as well, but often it's just going to be n. Okay? And we already talked about finite and the term for a sequence. That just means we could find the 7th term, the 20th term, the 200th term, and there's formulas for all this. Okay, so nothing to really think about or worry about. Okay, so right here, moving down, is a typical sequence formula. This is called an explicit formula. Okay, has an explicit formula which is very similar to slope-intercept form. Right? So if you look at this and you think of a sub n as being like a y, right? This looks strikingly similar to y equals mx plus b formula, which it is. And if we were to graph it, it will come out to be something that resembles a straight line. Right? And they're just saying, find the 12th term, or a sub 12 just means plug in 12 into this, nothing more. Okay, so if we plug in 12, a sub 12, for each of these n's, you just replace it with a 12. Of course, add those up. 144 plus 3 is 147. So the 12th term would be 147. Some people also think of it as like f of 12. F of 12 is 147. So a lot of the same mechanics, just for sequences. It has its own little way of being written. That's really what you want to focus on. And make sure you do have a sub 12 equals 147. I don't think we have any of those people anymore that just write answers and they don't write x equals, right? We have to write, what is this answer? It's a sub 12. You have to have both, a sub 12 equals. Right? Especially on AP tests, right? They want to have all the details, right? So right here, they just ask you to find the first 4 terms of each sequence. So that means first 4 terms would be a sub 1, a sub 2, a sub 3, and a sub 4. So you just write that out. A sub 1, what does that equal? But it's asking you to do it 4 times. All right, so you just have to plug in 1 for the first one, and 2 for the second one. All right, so of course, all we're doing is, of course, these values, that n and this n, these are the same thing. Right? Those will match, always be the same. And just simplify. Let's see here. I can't see you. There we go. So we have 3 minus 4, negative 1. And 6 minus 4, 2. Just keep on going. And notice once you get to the end, you can identify like that this is almost like a slope, and you'll notice the difference between these. If you do that, well, that's plus 3, that's plus 3, that's plus 3, right? Very similar to a slope. The difference in the slope are somewhat of the same thing. Now, that's not always the case. Sometimes you have something like this, which if you find the first 4 terms, a sub 1 is 5 to the negative 1 to the first power, which is just 5 minus 1, 4. While a to the second power will be 5 plus negative 1 to the second power will be 5 plus 1, 6. However, it's different from part A because as soon as you go back to 3, you got 5 plus negative 1 to the odd power, which is going to be negative 1 again, and you're back to 4. So sequences can have this pattern of like a straight line, but they don't have to. They can have something like this, which clearly this would not be a straight line. It's not of that format, that mx plus b. So don't always assume it just comes out to a straight line. So this sequence just tends to bounce back and forth between 4 and 6, 4, 6, 4, 6. Right? Or you can look at it as 5 plus or minus 1. Also another way of thinking about it. Okay, so try that on part number 3. Try on part 3. This one says write out the first 3 terms only, not 4, and then find the 11th. Plug in 11 and see what you get, and just use all the proper notation. Go ahead and try that now. All right, so we should get those answers, and we did fix this little number right here as well. So as long as you have, this is like the bare basics of what you could be accepted. You have to write a sub 1 equals, a sub 2 equals, a sub 3 equals, not just the numbers. Right? That's the bare minimum. You got to have both sides. Same thing here. A sub 11 equals 54, right, with the work that you use to get that answer. That's the bare minimum. All right, so let's go down here. All right, so we have, you saw there's some that are arithmetic that kind of look like a straight line, like mx plus b format, and there's some that don't. So we're going to look just at the ones that look like straight lines, arithmetic. And so just think those as one and the same. And there's different forms. We have a general form, which looks like this. This is a general form. Explicit looks like slope-intercept form. But this format and this format, you might notice that this is very strikingly similar to mx plus b, right? Where a sub 0, well, where x equals 0, that's a y-intercept. So an a sub 0 and a y-intercept have very similar functions. And same thing here. This is like a general. If I move this a sub k over, and I did this, a sub n minus a sub k equals d times n minus k, that is very strikingly similar to y minus y1 equals m times x minus x1, a point slope. So it's considered a more generalized version of where you can use any point of any on the sequence to get your answer, whereas this one you have to use the y-intercept. And you guys noticed, especially in this class, we use point slope a lot more often because rarely do we care what's going on at the y-intercept. It's really more on x-intercepts and things like that. So this one is just the same, but know that they are equivalent. So if you graphed it this way or solved it this way or solved it this way, you do get the same answer. So there are multiple ways of doing it. It's important to know that our sequence actually starts on the first a sub 1. So even though we do have a sub 0, that doesn't have an actual meaning in the sequence. If you graph it, like I'll graph it right here somewhere, right there, over here. If I was to graph sequences, they look something like this. That's what it looks like, where the first term is this number, the second term is this number. it does follow a straight line linear pattern, but there's no such thing as the 1.5 term or the 3/4 term, and that's why they're just dots at those specific values, because there's nothing in the middle. That does not exist. Okay, so that would be, and notice how sub-0, even though if I continue this, I could get a y-intercept, it's not graphed because the sequence starts on the first term, not on a 0 term that doesn't really have a meaning. Okay, but we do use that 0 term when we're doing this, right? We do use it as like a y-intercept, not because it's a real thing on the sequence, but just that it helps us get the formula for everything else. All right, so that's what we have. A couple different formats, very similar to what we already know. All right, so we can use that. It says, is a sequence an arithmetic sequence? So there's this rule up here that basically if the differences are the same, you subtract those differences, kind of like the average rate of change, like we did in the last one. If you check the average rate of change or the slope, it has to be the same between all the numbers. So you could do that right here. You could check these and say 5 minus 1 is 4, and 9 minus 5 is 4, and 13 minus 9 is 4, and so on. So we could double check just to make sure, yeah, it is indeed arithmetic. So that means the distance equals 4. Okay. And we need an a sub 0, that first term. Now, it doesn't give it this. The first one that it gives us is a sub 1. So we could just continue this pattern the other direction and say, well, to continue this pattern the other direction, I need a -3 right here. Right? So -3 plus 4 gives us 1, plus 4 gives 5. So my a sub 0 is just going to be using that difference or that slope and going 1 below. And then much like slope-intercept form, I have a slope and I have a y-intercept. I have a difference and I have a 0 term. So you can now write this formula. And that's all it asks for, so we can do that. Just note that if we want to use the other rule, right, what would that look like? So this format, I could pick any term, right? This is like x1, y1, so I could pick any term I want and just replace it, like my x for k and the actual term for a sub k, and that would work as well. So I could do this and say, yeah, a sub n would equal, and if I just picked, like right here, I'll pick 1. It could look like this, 1 plus a difference, n minus 1, and that would be equivalent as well. And much like if I converted point slope to slope intercept, I could distribute this and combine like terms, and I would get the y-intercept version. Okay, so they are compatible. They do the same thing. I just picked a sub 1 equals 1. That's why both of these are equal to 1. But I could have picked a sub 3 equals 9 and put 9 here and then 3 here, and it gives you the same exact thing. All right, so let's find the 46th term. All right, so find the difference. What is it? All right, 3. All right. And what is the 0 term? Use that to -1. So what is the explicit formula? A sub n equals 3n minus 1. And now that we have that, we can use that to find the 46th term. Just plug it in. Plug in 46, see what you get. So the 46th term, which is the same as a sub 46, that stands for the 46th term, will be 3 times 46 and minus 1. So that is 120 plus 18, 138, minus 1, 137. All right, so try number 6. It's actually the same steps as number 5. The wording's different, but as you guys know in math, after you critically read some questions that seem very different, once you get down to it, they turn out to be the same as far as how to solve it. So go ahead and try number 6 with 5 as the model. All right, so we got that. Negative 32. So try also 7, A, and B. So we have those, and let's look at the last one here, which is a typical problem for arithmetic sequences. It's the old movie theater seat problem, where they tell you that the number of seats in the first row is 16, or the first 16 rows arena form an arithmetic sequence. If there are 20 seats in row 1, 23 in row 2, how many seats in row 16? And so let's say our sequence starts at 20, goes to 23, and then dot dot goes on for a while, and then it's asking you how many right here are at the 16th row, A sub 16. So same thing, you can find the formula, plug in 16, and get a number. So what is the difference? What is the sub 0? So nothing more difficult than you've already done. We got a difference of 3. A sub 0 of 17. And you do the rest. Now there may be different versions of this. They may not give you like what the first row is. They might give you what the 6th row is. So just know you can use the other version of the formula and solve it just as well. So we do have like it's kind of like the point slope version, where it'd be like a sub 1 plus the difference, n minus 1. We could use this as well, where it doesn't have to be the first, it could be the 6th term, and we could do n minus 6 and whatever the 6th term is. So if it doesn't give you like the first, second, third, and it gives you other information, you might have to use this version, which is like point slope, meaning you can use any number sequence anywhere, not really the first one, which is easy to get to the 0. So if you can't get to the 0 term easily, you probably want to use this, and it would work just the same. So here, a sub 1 equals 20, right? So for a sub 1, we'd have 20 and we can plug in 3 minus 1, and this would be a more general, right? And then we can find a sub 16, which would just be 20 times 3, 16 minus 1, which is 20 plus 45, which is 65. So you get the same answer regardless. If I use a sub 2, which is 23, I could plug in 23 here and 2 here instead of n minus 1, n minus 2. It'd give you the same exact answer. So it's not that necessarily you have to have the first term and be able to work backwards to get the 0. Like, it's not like we have to have a y-intercept to have an equation of a line, because point slope, or this version, lets us find an equation with any point, right? Not just the y-intercept. Okay? And there may be another question here. What if it asks you to sum up all the seats from rows 1 through row 16? So this is just row 16 by itself. How would you add up row 1 plus row 2 plus row 3 plus row 4 plus row 5 without finding them one by one? So you might have come across this formula before, and it looks something like this. Let's go pink. And if you want to find, add everything up, which the fancy word for that in math is the sum. So the sum of this many terms is going to be half of that number of terms, and then you just add the first and the last term together. So this just means first term, and a sub n means last term. So if you had the beginning and the end, you know how much was at the beginning, you know how much it was at the end, then you just have to add those together, take half of how many rows there are, and then multiply it together. So in this case, if I want to find the sum of 16 rows, that would be 16 over 2. And the first row seats 20. And we found out the 16th row is 65. So 20 plus 65. The first row is 20. Last row, 16th row is 65. And then if you do that, that's a fast way of adding everything up without having to find everything one by one by one by one. So that would take a while to do this problem right here. Plug in 1, what do you get? Plug in 2, what do you get? Plug in 3, what do you get? Go all the way to 16, and then after all that, add them all together, right? That would take a long time. This way, a lot faster. So we have 8 times 85, which comes out to be 64 plus 40, 640 plus 40 is 680. All right, so that'd be all seats, row 1 through row 16, assuming that took place. And you'll notice that right back up here, going back to here, that a sub 0, this doesn't have a meaning in the problem because there's no row 0. This is, if we try to rationalize this, it'd mean, oh, at the 0 row there were 17 seats because at the first row there was 20 and the second row is 23. But really there's no such thing as a 0 row. So just remember when you're actually graphing it and looking at the sequence, go back to this right here, you'll notice that, yeah, there could be a y-intercept here, but we don't actually plot that. The first term of the sequence is at a sub 1. So we use that a sub 0 to help us find out what a sub 1 is and a sub 2 is, but it's not actually part of the sequence. The counting starts here. N greater than equal to 1. It has to be 1 or bigger, and it has to be a whole number. There's no such thing as, oh, you're sitting in row 1.5. You're sitting in row 3.5. All right, so hopefully that adds some context on why we have only integers here, because in practical terms, it does not make sense. Those things do not exist. All right, so with that information, you'll be able to do homework problem set number 1. All right, so work on some of this stuff first, right? But you'll get through this and kind of like, as soon as you get the feeling, okay, I got this, because you're not going to be able to finish everything today, but as soon as you do a few of these, skip down and start working on some of these types of problems and try to get those done before you leave. All right, get that finished, and that way when you're done or later on when you're not in class, you just have the, kind of this more calculating work to do, and the word problems are all completed, or you've had time to ask more questions about finishing these, because this is really what you want to eventually get good at. All right, ready, set, and go.